Hello students, in this video I would like to discuss about divide and conquer approach, which is one of the algorithm design technique. Divide and conquer approach break the problem into several sub-problems that are similar to original problem but smaller in size. So here what we do is, here we have a problem. So we divide that problem into some sub-problems. And we are going to apply this same solving technique or the same recursive approach in the smaller problems also. So solve the sub-problems recursively and then combine the solutions to create a solution to original problem. So here we are reducing the size of the bigger problem and we are solving this sub-problem separately and we are combining the solutions. The divide and conquer approach involves 3 steps at each level of recursion. So in each level of recursion we have 3 steps. First one is divide. Here divide the problem into number of sub-problems. Next is conquer. Conquer the sub-problems by solving them recursively. So the sub-problem will be solved recursively there. If sub-problem sizes are small enough, however, just solve the sub-problem in straightforward manner. So when we subdivide the problems in different levels, at some point of time we will get the very small sub-problem which can be solved in straightforward manner. At that time we will stop that splitting into sub-problem. The third one is combine. Combine the solutions to sub-problems into solution for the original problem. So from the bigger problem we are getting some number of relatively smaller problems. So when we combine the solution of this smaller problem, we will get the solution for original problem. So this is the general approach of divide and conquer technique. So generally the complexity of many divide and conquer algorithms is given by the recurrence of the form t of n equal to 1 if n equal to 1, that is if size of the input is only 1, the running time will be constant. Otherwise it will be in the recurrence form a t n by b plus f of n. I already told you we are going to divide the bigger problem into smaller problem, where a means number of sub-problems. If a equal to 2 means I am dividing the larger problem to 2 sub-problems. If it is 4 means I am dividing the larger problem to 4. So again in these 4 sub-problems we are applying the same technique. First sub-problem will be divided into 4 again. Second problem will be divided into size 4 again. So similarly we are finding the solution. We will stop when we get the direct solution. And n by b is the size of each sub-problem. You just consider n as 10 and b as 2. So you just imagine 2t 10 by 2. That means we have a problem of size 10. We are dividing it into 2 problems, each of size 5. And f of n is the time for divide and conquer. Some time will be taken to implement these 2 steps also. For divide step and conquer step, that will be denoted using a function f of n. Anyway, it will be more clear when we see some examples. So here are some examples of algorithms which follows divide and conquer approach. First one is binary search, second one is merge sort, third one is quick sort. So here in this video I would like to discuss about binary search. So we all know the working of binary search. So first point, binary search is applied in a sorted array. The input to the binary search is a sorted array. So for searching anyway we need an array of elements and also item to be searched. First we compare the item to be searched with the middle element in the array. If the item is found there, our search finishes successfully. Otherwise, array is divided into 2 halves. So here we are dividing array into 2 halves. That means we are dividing a larger problem into half. First half contains all the elements to left of middle element. Second half contains all the elements to right of the middle element. Since the array is sorted, all the elements in the first half, that is left side of the middle element, will be smaller. All the elements in first half will be smaller than middle element. Similarly, all the elements in second half will be larger than middle element. If item to be searched is less than middle element, you have to search that item in the left half or the first half. Otherwise, you have to search it in right half. So the above steps are done recursively till we find the required item or get a partition which does not have any element. What's the meaning of last point? So when did this algorithm stops? The algorithm stops if we find that element. Otherwise, if the element is not in that list, what will happen? The size of the problem at some point becomes 0. then we are going to use pseudo code. So look at the pseudo code for binary search. Here the input is an array A whose index value ranging from 1 to n and item which is to be searched. Just notice the index value ranging from 1 to n, not 0 to n minus 1. And it has 4 parameters: array A, low value, up value and item. Low denotes starting point of the list and up denotes end point of the list. Initially low value will be 1 and up value will be n. So if low greater than up, that is the anchor condition. So this condition becomes true only when the element is not in the array. The mid is calculated using the formula ceil of low plus up by 2. So I hope you know the function of ceil. So you just imagine low is 1 and up equal to 16. So in that case low plus up will be 17. 17 by 2 is 8.5. Ceil means it will round up to the next integer. 8.5 will be round to 9. So that's the function of ceil. That's how the index value of mid element will be calculated. Then that mid element will be compared with the item. If it is matching, then we will return true. Otherwise we will check whether item is greater than a of mid. That means the element to be searched may be in the right hand side of the mid element. So the same search algorithm will be applied to the right subarray. So right subarray means the low value will be mid plus 1, next element to the mid. If item is less than a of mid, then that search will be applied to the left subarray. At that time end element of subarray will be denoted by mid minus 1. So that's the meaning of these two recursive calls. So here's an example. First example is for a successful search. You can go through that. And also the second example is for a unsuccessful search. So remember, the initial code for binary search will be a comma 1 comma n comma item, because the index value of this array will start from 1 and ends at n. Next we are moving to analysis of binary search. So here I have the pseudo code. So we already discussed about how to analyze recursive procedures. So let t of n be the running time to execute binary search, because here we already discussed the initial value of low will be 1, up will be n. That means we are applying binary search to n elements. So line number 6 to 9 takes almost tn by 2 since only line 7 or 8 execute. Here either this call will execute, otherwise this call will be executed. In the same recursion, these two calls will not be executed, only one call will be executed. So you already saw the list is getting divided almost by 2, not exactly by 2, it is almost by 2. So this on recursive call will take tn by 2. So line number 1 to 5 takes constant time. Here these line number 1 to 5 are independent of n, so it takes only constant time. So I can write the recursive equation as t of n, that is running time to execute binary search to entire array, equal to tn by 2 plus 1. Here I am splitting the problem into half the size, but only one half is considered. That's why here it is tn by 2 plus 1, since it is this line 1 to 5 is a constant. So you already solved this example. So t of n will be O log n. So that's the worst case. So what about the best case? You just imagine in the first call itself the middle element equal to item. Best case occurs and middle element of input array and item are same. So input array means it will contain all the elements, and if the middle element of that array and the item will be same, best case will occur. At that time it will execute only line number 1 and 2. That's why best case is big O of 1. So we will discuss the remaining examples later. Thank you.